All right, class, so here is the explanation video for this energy transfer problem. I think this is a really great problem. It is a simple problem, but it's sort of pretty complex to solve. So let's go ahead and get into it. So what's going on here, we've got some amount of hot water essentially and some amount of cold water, and we're going to mix them together. This is an experiment essentially that you could do at home. You know, you can mix hot water and cold water, and we know that the final temperature is going to be somewhere in between 85 degrees and 15 degrees Celsius, right? Just common sense essentially tells us if I mix this hot water with this cold water, I'm going to get some final temperature of my water that's going to be in between those two temperatures, and then this calculation will actually allow us to solve that exactly, so we'll know exactly what that temperature should be. So the setup that I might do here, I like drawing, obviously a little picture. So I'm going to draw a picture that looks like this. I'm going to say that this is my 350 milliliters of 85 degrees Celsius hot water. And then down here will be my 275 milliliters of 15 degree cold water. So obviously not to scale, but you get the idea. We've got our hot water here, we've got our cold water here, and there's going to be a transfer of energy. There's going to be a transfer of energy from the hot water to the cold water. So this would represent my transfer of energy, and we're looking for what the final temperature is going to be after this transfer of energy has taken place. Okay, so what we can sort of think about is that this energy transfer, the energy lost by the hot water will be gained by the cold water. That's sort of how the energy transfer works, right? And so whatever amount of energy the hot water loses, the cold water is going to gain that amount of energy. So we could say that the energy lost by the hot water is essentially going to equal Q equals S times M times delta T from the point of view of the hot water. So when I say Q, that's going to be the amount of energy, and then I'm using SM delta T here because we're talking about a certain quantity of water, right? If I look at that specific heat, I've got the units of grams in there. That's going to tell me, we need to use this Q equals S times M times delta T. So if I wanted to write this out, the energy lost by the hot water is going to be equal to 4.184 times 350. So now here I'm using 350 grams instead of 350 milliliters because the density of water is 1 gram per milliliter. So whenever we see that, we can just do that quick conversion there. They're going to be the same. And then here I'm going to write T final minus 85 degrees Celsius. So we don't know what this change in temperature is because we don't know what the final temperature is. So in this case, we do need to write T final minus 85 degrees Celsius. So this calculation here is going to represent the amount of energy that's lost by the hot water. This is going to be a negative value, so I know that T final should be between 15 and 85. So this whole thing is going to end up being a negative value for energy that's lost by the hot water. Now we can conversely say, what about the energy gained by the cold water? Again, we're going to use Q equals S times M times delta T. And that's going to equal 4.184 times 275 in this case. 275 because we've got 275 milliliters of that cold water. T final minus 15 degrees in this case. And again, this T final, that should be the same, right? Because all of this energy that's transferred is going to be transferred to the cold water, and the final temperature for both should be the same. Again, this is going to be assuming that no energy is lost to the surroundings. We're going to be saying that this is perfectly insulated. So if you've got a good thermos, this would be somewhat reasonable for sure. So now we've got this equation, and now this equation here is going to be positive, right? We're going to have a positive amount of energy because it's energy gained by the cold water. Now, the relationship between these two equations is that the value, the quantity, should be the same. The amount of energy that's lost should be the same as the amount of energy that's gained, but the sign is different. So remember how we've been switching the signs whenever we're talking about from the point of view of the reaction or the point of view of the calorimeter? The same thing's going on here, so we need to change the sign. So the way that I would do that is I would probably just introduce a minus sign. I might say, I'm going to multiply this whole thing by -1, and then now each one of these will be positively, have a positive value, and I can set them equal to one another. So let's go ahead and do that. So the last step here is going to be to say, I'm going to write -1, 4.184, 350, T final minus 85 degrees Celsius is going to be equal to 4.184, 275, T final minus 15 degrees Celsius. And we've got one equation and we've got one unknown. T final is our only unknown. It should be the same for both. And again, this -1 here is just to make them so that the signs are the same on both sides, that this value will equal exactly what this value is. So now we need to do a whole bunch of algebra and solve this problem. So I'm going to walk you through the steps that I actually did when I worked this out. So the first thing I did is I multiplied these two values together and I got -1464.4. So that's this right here. T final minus 85 degrees Celsius is equal to 1150.6. T final minus 15 degrees Celsius. So here, just multiplying those together. Then I'm going to sort of distribute this out. So -1464.4 times T final. Now plus, so a minus times a -85, that's going to be plus 124,474. And that's going to be equal to, on this side, our T final. And then now in this case, it's going to be minus, so a positive times a negative is going to be minus 17259. Now I'm going to sort of group things together. So I'm going to be adding this 17,000 to this side and adding this 1,400 to this side. So that will end up being 141,733 equals 2,615 times T final. Now solving for T final, I get 54.2 degrees Celsius. So just a quick double check. Oh, sort of got cut off there. Quick double check. Does this answer make sense? Right? Is it between 15 degrees Celsius and 85 degrees Celsius? Yes. So that seems reasonable. What are we doing here? Sort of setting these equal to each other. We're saying that all of the energy that's transferred away from the hot water is gained by the cold water. We introduce this negative sign just because it's got to be the signs have to be the same, and so from the point of view of the hot water, it's losing that energy. It would have a negative value of energy, and from the point of view of the cold water, it's gaining the energy, so it would have a positive value. If I want to set those equal to each other because the value will be the same, then I need to introduce a negative sign to sort of make the math work out. There are other ways to do that. So if you did it in a different way, that's totally fine. But this is an easy way that I like to show that. So hopefully that makes sense. If not, let me know. This is a great question. All right.